Hello. Well, back to topic 5. So far, you should have looked into the previous clips or videos on Ohm's law, Kirchhoff's law, and divider's rules. Okay, so you are here again with me, อาจารย์ Patamaporn, okay, at Kasetsart University, Bangkok, Thailand. And this topics number 5 will be on nodal analysis and just nodal analysis, I think, just for now. Okay, so to start off with the analysis, the first analysis that we're going to do is I want to review Cramer's rule. Cramer's rule. Well, Cramer's rule is a method to solve a simultaneous equations using determinants and matrix. Okay, of course, your calculator nowadays is also able to solve the simultaneous equations. Okay, you simply have to type in the equations, okay, and they will solve the unknown parameters for you. But I will tell you anyway, okay, of how we can do it by hands, okay, and a little help of calculator, of course. Okay, so the simultaneous equations are, for example, if you have these two unknowns x1 and x2, you have two unknowns x1 and x2, and you have two equations, right? You have to have, if you have two unknowns, you need two equations to solve the problems. So the first one, the first equation is, right, a11 x1 plus a12 x2 equal to b1, and the second equation is a21 x1 plus a22 x2 equal to b2. Of course, you know, if you put in numbers, it would be something like this. Okay, maybe 2x1 plus 5x2 equal to 4. Or another equation would be x1 plus 3x2 equal to 6, for example. Okay, you have to solve for, and you have to solve for x1 and x2. Okay. Well, of course, there are many ways you can do this. I'm sure you have done problems like this since your middle school to find x1 and x2. But this is another way using Cramer's rule, using matrix. So what you can do is, of course, after you have these two equations, you can transform it right into matrix form. Okay, so you put the factors a11, a12, a21, a22 into a matrix form, right? And then multiply by x1, x2 in this form equal to b1, b2. So in the example, it would be, right, 2, 5, 1, 3, right, x1, x2 equal to 4 and 6, like this. Okay, so this, you get a 2 by 2 matrix. Okay, and to find x1 is that you have to take determinant. You replace the first column of your A matrix. Okay, you place the first column, okay, with this matrix right here, b1, b2. Divide by the determinant of the matrix, you know, the factor A itself, okay, the factor A itself, right, the determinant of that, okay. And of course, the way to do this is you multiply, you know, diagonally, so b1, a22, right, and then minus b2 times a12. Okay, same thing here. So multiply a11, a22 minus a21, a12. So in this case, x1 would be equal to the determinant of, right, 4, 6, okay, and 5, 3 divided by the determinant of 2, 5, 1, 3, like this. Okay, and it would be 4 times 3, right, 4 times 3 minus 5 times 6 divided by 3 times 2 minus 5 times 1. This would be x1. You get your answer. Okay, right, so this is okay, we have example here also. Okay, so you take the factor in front of your unknown parameters, put in term of matrix, okay, and this become this matrix here, okay, and then your v1 would be the determinant of, replace 6 and 4 into the first column, right, okay, and then multiply, you get 2 volt, okay. V2 is you replace that B1, B2 column into the second column, okay, of your matrix, and then get the answer. So V2 is minus 1 volt. So this is the Riemann-Kramer's rules. Okay, of course this is 2 by 2. You can have it 3 by 3 matrix also. You have 3 unknowns and then 3 equations that you have to solve. So it's the same thing, the same concept, right? You are the factor, the A factors right here, A11, A12, A13, put in term of the matrix here, okay, and B1, B1, B2, B3 becomes this matrix. Okay, and to find x1, x2, x3, right? x1 you replace column 1, right, with b1, b2, b3, and x2 you replace column 2, right, with b1, b2, and b3, and x3 is you replace b1, b2, b3, oh it should be 3 right here, sorry, mistake, okay, into column 3, and you find so-called the determinant. Okay, so and to find this determinant, if you sort of forget, okay, the way I do it, so look at this example, I1 plus 2I2 plus I3 equal to 6, right, the first equations, and second equations is this one right here, I1 plus 2I2 minus 2I3 equal to 1, and the third equations, I1 minus 2I2 plus I3 equal to 0. Okay, so you take the so-called factor in front of your unknowns, put into this matrix right here, right, and your 6, 1, and 0 become this, put into matrix form like this. And when you want to find a determinant, right, you want to find I1, you replace 6, 1, 0, you replace the column number 1, first column with 6, 1, 0, so here it is. Okay, and the way you find the determinant for 3 by 3, the way I do it, I just extend the first 2 columns, write it like here and here, right, 6, 1, 0, 6, 1, 0, 2, 1, minus 1, 2, 1, minus 1 here, same with at the bottom, the determinant of this matrix here, 1, 1, 1, 2, 1, minus 1, 2, 1, minus 1, and you do the multiplications, the red one, okay, take the positive sign, right, so the red one, so 6 times 1 is 6, 2 times minus 2 times 0 is 0, right, and 1 times minus 1 is minus 1, right, and then subtract the multiplication of the other way, okay, the blue color, so 0 times 1 is 0, right, I didn't write it down, and 2 times 6, 2 times minus 2 times minus 1 become 2, 2 times 6 is 12, we can put it minus 12, subtract 12, and this is what, 2, right, 2 times 1 is 2, so subtract 2, divided by same thing, right, the downwards diagonal downwards is positive, right, plus sign, and then you minus whatever in the blue multiplication of the along the blue dotted line here, okay, and you get the answer I1, and you can do, well, would be amps, supposedly I1 I2 is for current, okay, so this is you can go and copy this, write down the problems and go and do the multiplication, practice by yourself, okay, but of course you can go and learn from your calculator also how to do this, okay, I wouldn't mind. And next one, okay, so nodal analysis, okay, nodal analysis, so we're going to do nodal analysis now, okay, so there's a so-called method or procedure of how to do it, so you can like start it off correctly. So these are the procedure, the method, the steps to perform nodal analysis in a circuit, okay, so first you look at your circuit, you determine number of node in a circuit, okay, second one, you select one node as reference, usually ground, okay, third, assign voltage and currents, okay, at each node and where, especially where the node voltage is unknown. Okay. Step 4, apply KCL at the unknown voltage nodes. Okay. 5, express the KCL current equations in terms of node voltages. And number 6, we solve for node voltages. So in another way, at the end, if you perform nodal analysis, you would get the node voltage. Okay, node voltage of the problems. Okay, so another review here, for example, so what are the nodes and what's the reference node? So therefore, in this picture, you see that we have 3 nodes altogether: node A, node B, and node C. And for simple sake and all the book, sort of like if it's not written where ground is, okay, we always assume that it's like at the bottom of the circuit right here. Okay, in all the exercises, problems in the lectures or in the textbooks that we use. Okay, so therefore, so let's start. If this is an example of we want to find node voltages. Okay, node voltages, in this case we want to find VA. Okay, so therefore to start, okay, so let's say that I have just this circuit, right? Before I'm going to do the step according to the step that we had written above. Okay, so R1, R2, R3. So if you're given these circuits and you are asked to find node voltages, okay, node voltages. Okay, so first of all, you have to, it say that number 1, right, determine number of nodes. So where are your nodes? So therefore, well, I said this is one node, give it a name, okay, node C, okay, node A, node D, and of course that's this node right here, right, this node right here. Well, the second step say that one node as reference, right, normally ground. See, so therefore we would I choose that this is my reference node. Okay, so we always 0 voltage there. Okay, so now what do I next? What I go, okay, do I know any does the problem already have given any node voltages? So I look, okay, so okay, VC, the voltage at VC with respect to ground is equal to VS1, okay, and VD is also, I also know that from point D to ground it's VS2, so I know that the node voltage for point C and point D is as according to what I just written. Now the one that I don't know then is VA, right? So I don't know VA, so we're going to find VA. Okay, the step, what did the step say? The step say that, well, assign voltage and currents at each node when node voltage is unknown. All right, so I'm going to sort of like try to figure out, assume first how the currents flow in this circuit. So I will say, okay, I have a circuit here, come out from VS1, right? And this is called IR1, okay? And of course, when there's a current flow, through, oops, sorry, blue, different blue, okay? When there is a current flow, right? Okay, let's call it IR1, okay? There's a voltage drop across R1. I'm going to call it VR1, okay? Right? Well, there's another current, I'll say come up from the positive right here. So this is IR3, okay? Well, when it passes through R3, it results in a voltage drop, VR3 like this. And then IR1 and IR3 comes together at the junction at the node A, and maybe the current can flow out down like this. So IR2, and so there's a voltage drop right here, VR2. Okay, so this is what a good practice for writing, to do the problems. You see, you sort of give a sign where your currents go and where's your polarity of your voltage drops are. Okay, then what did it say? It said that, so I did number 3 now, right? Assign voltage and currents at each node where node voltage is unknown because node A we don't know. Apply KCL at the unknown voltage nodes. So I'm going to write KCL at node A because I don't know node A. The other node I know already what the voltages are. So KCL at node A, right? KCL is Kirchhoff current law, right? You add currents that go in and out node, you add current, right? C, current, you add current. So therefore, IR1 is going into node A, so I give it a positive sign, okay? IR3 also entering, so plus IR3, but IR2 is leaving, so minus IR2 equal to 0. So I get my equations from applying KCL, okay? But then, what is it? Well, the voltage, the question asks for node voltage, but the question you get now is in current form, right? So therefore, you have to transform this current IR1, IR3, IR2 in terms of node voltages, right? See, number 5, step 5, express the KCL current equations, okay, in terms of node voltages. Okay, so let's have a look. IR1, let's look at IR1. Okay, IR1, if you look at it, IR1 is Ohm's law. Go back to Ohm's law. IR1 is equal to VR1, right? I equal to V over R over R1. Correct? IR1 equal to V drop across R1 divided by R1. Well, the voltage drop, well, it's still not on the so-called node voltage term because node voltage would be, well, V at point A, V at point C, and V at point D. Okay, these are node voltages in terms of VA, VC, and VD. So what is VR1 then? Okay, VR1. So VR1 potential difference, right? It's a potential difference, okay, between one point to another point. So VR1, we would say that, well, it's a potential difference between potential at point where the positive sign is, right? C, VC. Difference means you have to choose a subtract, right? Minus the voltage drop at the negative signs right here, where the negative sign is, so it's VA. So therefore, VR1 is VC minus VA over R1. You see that? Okay, now you have it IR1 in terms of node voltages. So therefore, okay, what about IR2? Let's see. IR2, right? IR2 would be, well, VR2 over R2. But VR2 is nothing but, if you look at the picture again, right? It's the voltage drops between, here the positive here is VA, and minus this potential at this point, at the negative terminal here of VR2, okay, which is 0. So therefore, VR2 is simply VA. So it's VA over R2. Okay. What about IR3? IR3, right? IR3 is V drop across R3, right? So V3, V drop across R3 divided by R3. Well, V drop across R3 is the potential difference between this point, right? Positive here, VD minus VA. Right? And VD is VS2, so therefore, right, this is VD minus VA. VD is VS2, okay? So therefore, we can substitute VD equal to VS2. And this one is, of course, VC minus VA. So VC is VS1, okay? So therefore, you would get your equations at node A, okay? Now, in terms of node voltages. And of course, you can put in the value of VS1, put in value of VS2, R1, R2, and R3, and you can solve for VA. So you get all the node voltages. So this is the concept of node voltage. Okay. So for another example here. Okay. Another example. A little longer. Okay. The problem is a little longer. Okay. So therefore, same thing, right? See. You have Vs1 given here, Vs2. So how many nodes are there? There are 1, 2, 3, 4, and 5 right here, right? And of course, choose one as reference. So the one at the bottom here, right, as reference. So V equal to 0. Okay. Assign the names VA, VB, VC, VD. Okay. The current in and out as you wish. In this case, what they do is they go like this. Okay. The current comes here, divide into IR2, IR3, IR3 divided into IR4 and IR5. Okay. So that's the case here. See, it doesn't have to go like, it can go like this also. It really depends on you. If the question is not given anything to you, you can assign, the current flows by yourself. Then, what's next? Well, we got the current flowing. Now, do we know does the problem give any node voltages? Well, it did, right? It give VC. VC is VS1. Which is 4.5 volt. VS2, VD is what? Minus, right? Minus VS2 because you see that it's flipped. Okay, it's not positive and negative like this. It's actually flipped. So therefore, VS2 is 7. So therefore, VD is equal to minus 7 volt. Okay, you have to be careful. See the importance of sign for the voltage. Okay, so therefore, VC is 4.5, VD is minus 7. Then right now, so the only one unknown node voltages are VA and VB. So we're going to solve for VA and VB. So we have to write KCL at node A, VA, node VA. Okay, so IR1 going in positive, IR2 is leaving, so minus IR2. IR3 is also leaving node A, so minus IR3. So equal to 0. Okay, then KCL at node B, right? IR3 going in, okay, minus IR4, right? Leaving the node B. IR3 leaving a node B, IR3 equal to 0. Okay, now we have to, of course, change all this IR1, IR2, IR3, IR4, IR5 into node voltages. Right? So therefore, IR1 equal to IR1. So look at IR1. IR1 is here, right? So positive current go into the positive, leave on a negative. So positive here, negative here. So the potential difference that go across R1 would be VC. Right? It's the potential difference between VC and VA. So VC minus VA, and VC happened to be VC 4.5. So it becomes VS1 minus VA divided by R1. So equal to 4.5 minus VA. Okay. IR2, right? IR2, current across R2. So the voltage drop across R2 is simply VA. So VA divided by R2, which is 680. Okay. IR3, VB, right? IR4, right? IR4 is voltage drop across R4, which is simply VB divided by R4. IR3, right here, IR3. So IR3, the voltage drop across R3 is the potential difference between VA and VB. So it's VA minus VB, right, over R3. IR5, look at IR5. IR5 is, right, V across R5 is the potential difference between VB and VD. So, right, VB and VD, and VB minus VD, actually VB minus VD also, you can say that, right? But VD is minus 7, so minus 7, okay, minus 7. So therefore you get that. So you would get from node A, so this is the equations, right? So IR1 minus IR2 minus IR3. Please be careful when you have like this minus sign, you have to do subtraction, please write down the parentheses, okay, so you won't make a mistake when you solve, for the problems, okay. So you get, you have to do your math, okay, you get this. And this is your KCL in terms of node voltages at node B. And then you use these two equations to solve these two equations to solve for VA and VB. Okay, that's how the nodal analysis goes. All right, okay. Well, I'm going to, how about you write down these problems right here. I'm going to give you some times to copy this problem and you solve for VA and VB. Okay, give you 2 minutes to copy it down. Leave some space in your notebook, okay, and solve the problems. Well, you can pause it, right? Pause and then copy it. Okay, pause my video and copy the problems. Well, the problem is, well, I'm going to give you, I don't know if you have the answer. You can check, if this, I even got the right answer or not. So VA is about 1.667 and VB equal to 2. Okay, all right. So, okay, so there are different problems, okay, different exercise, okay, that you can do. Now, this one has dependent source V1 over 16 as a current source. So this is the voltage control current source. So you may need a little more time to solve for this. Okay, all right. Okay, so let's move on. Okay, this is something that we can do later when we meet each other in class. Okay, or next one, okay, supernode. Okay, to do nodal analysis, sometimes you have to look at the problem a little more carefully and see if there's any shortcut for you, and one of the shortcuts is called the supernode, make your so-called problem easier. So supernode is formed by enclosing a dependent or independent voltage source connected between two non-reference nodes and any elements connected in parallel with it. Okay, sound like what? When you when I read it or you read it. Okay, a supernode is formed by enclosing a dependent or independent voltage source connected between two non-reference nodes and any elements connected in parallel with it. So this is a general term for supernode. Okay, so I'm going to show you and what it is. So let's look at this one here. Okay, so this problem here, okay, this circuit here. So you see that there are two voltage sources. Okay, well, where are the nodes? Nodes here, V1, node V2, node V3, and the reference node, down at the bottom. Okay, well, it says that, well, do we have supernodes, right? Well, this one, for us, we don't consider it supernode because one is, of course, non-reference node, but the other node is reference node. So we don't consider this as a supernode. Okay, but the second voltage source, you can see, okay, it's connected, right, between V2 and V3. V2 is non-reference node, V3 also non-reference node. So therefore, this is supernode. So supernode is when we enclose V2 and V3 together like this. Okay, so V2 and V3 becomes the supernode. Okay, so what is so useful about this supernode? Okay, so it would save you some time because what it is that, okay, if I write down, what you have to do is, so normally we would say, okay, I don't know V1, I don't know V2, I don't know V3, right? So I have to write down KCL for all three nodes, unknown node voltages. V1, KCL at V1, KCL at V2, KCL at V3. But whenever you have a supernode in the questions, in the questions, you can simply write the KCL for V1 in this case and KCL at supernode. Let me write down, it's a supernode, okay, SN, supernode. Okay, so let's see. So if I write down KCL, okay, at V1, so KCL at V1, right? I have all the current flowing, okay? I'm going to do it real fast, okay? So therefore, change it to the node voltage right away. So therefore, KCL at V1 would be, right? So it would be I1, right, minus I4, right? Well, actually, wait a minute. We don't even have to write V1, correct? Because V1 I know is equal to 10 volt already. Oh, sorry, okay. So V1 is already 10 volt because we know that it's right here, right? Here, node voltage V1 is 0. So therefore, we have to write at supernode, okay? So we don't have to write KCL at V1. So therefore, we KCL at supernode, right? So you look at the current going in or leaving that, red circle that I put it as supernode. So I1 entering a supernode. I2 is leaving supernode, so minus I2. I3 is leaving a supernode, so minus I3. And I4 entering supernode, so I4 plus I4 equal to 0. So therefore, change to node voltage. I1 would be, right, V1 minus V2 over 2 minus I2 is V2 over 8 minus I3 is V3 over 6 plus I4 is V1 minus V3 over 4 equal to 0. Okay, but we know that V1 is equal to 10. So therefore, this becomes 10 minus V2 over 2 minus V2 over 8 minus V3 over 6 plus 10 minus V3 over 4 equal to 0. Okay, so therefore, you have two unknowns, V2 and V3. But then if you have two unknowns, you need another equations to solve the problem, correct? Right? So where is that another equation that would help you? Well, it's at supernode, right? So supernode tells us that, oh, okay, so between V2 and V3, the voltage value is this one, the voltage source right here. So if I say that this is, let's say 5 volt, this DC source has 5 volt in. So my another equation would be V2 minus, right, I take V2 as positive, right, because it's positive here, minus V3, right, equal to 5. So this is my second equation. This is first. This is second equation for me to solve. So do you see what I'm saying? So therefore, you can either say, okay, then my V2 equal to 5 plus V3 and substitute it back into equation number 1, right? So everything would be in V3 term and you can find V3. Right, so therefore, this is how supernode can help you to reduce in solving the problems, reduce the time. Okay, so same thing here. Okay, so same thing with these problems right here. So you have, well, of course, this is V1, right? Node voltage equal to 5, right? Current source is not part of the definitions as supernode, so we leave it there. But this one here, 4 volt is connected between this node and this node, non-reference node. So therefore, this is your supernode. Okay, you can copy this and try to solve the problems here. Okay, and tell me the answer. Talk to me online or something. Tell me what V2 and V3 and V4 is. Okay, so therefore, there are many problems, okay, exercise you can go and find out, okay, right? So for example, this one also, okay, so you can see that the supernodes right here, so VB minus VC. So information you get from supernode is VB minus VC equal to 24 volt. Okay, you can find that too. Now another, let's see. This is another example to show you that supernode. Remember one of the definitions say that the last portion of the definition and any elements parallel to it. Okay, Supernode is when you have water source connected between two non-reference nodes and any elements connected parallel to it. So this is an example. Okay, if you have, in this case, you have 10 ohms connected in parallel to this 2 volt, which is connected between V1, V2, which are non-reference node. So therefore, your supernode is all this. You can consider all this. So therefore, if you write down KCL at supernode, it would be, well, 2 amps going in, right? 2 amps going in positives, right, to supernode. Okay, and I1 is leaving, so minus I1. I2 is leaving, so minus I2. And 7 is leaving. 7 amps leaving, so minus 7 equal to 0. So this would be as simply as that. Okay, so it will become 2 minus I1 is V1 over 2 minus I2 is V2 over 4 minus 7 equal to 0. So equation number 1. Right? Equation number 2 that you have to use, of course, would be, right, positive is here, right, the water source, so V2 minus V1 equal to 2 volt. So this is your second equation, and you used 1 and 2, equation 1 and 2, to solve for V1 and V2. Okay, and well, this is how you do it, and this is the answer. Okay, right, so please go and do it yourself on your own free time. Take your time to understand it. Okay, that's the answer. So therefore, this session, this topic is over. It's only on nodal analysis. So the next one will be on mesh analysis. Okay, thank you. See you.